Yeah, thanks. Wonderful. Thanks for the way too kind introduction. So thanks for the kind invitation as well. And thanks to the organizers, in particular to Ursh, for all the effort and sweat of setting up this beautiful meeting on tensor product methods for strongly correlated molecular systems. And also specific thanks for the honor of giving this colloquium talk of the meeting, even though I must admit I'm not quite sure what that is. I took it as an impetus to provide a bit more of a broader overview, be a bit more motivating and introductory, and also be a bit more accessible to a non-specialized audience. So when we go on a journey leaving the familiar, warm, and cozy physical corner, when we have a look at tensor network methods augmented by mode transformations in molecular quantum chemistry and condensed matter physics. But in fact, when we meander through the theme in this colloquium, I will take the liberty of meditating also a bit about the theme of the physical corner, as well as in other contexts and perspectives of using tensor network methods, say in notions of quantum simulation, probabilistic modeling and machine learning, or in notions of holography, depending on how it goes with time. So this comes at the price of being a bit superficial. Apologies for that. But I guess for this kind of talk, this is presumably more than a feature than a bug, so I hope. Okay, so the reason why we are all here, at least virtually in these awkward times, I hope you're all well, is that tensor networks are a concise description of natural entangled states of matter. A statement that truly applies to strongly correlated quantum systems and materials. And while this may sound a bit like a propaganda message, the truth value is actually quite high, as we will see now, and as you have already seen during the day. And here's the thing. So manybody state vectors, they live in enormously large configuration spaces, vector spaces, Hilbert spaces that grow exponentially with n the number of degrees of freedom, so the system size of the problem. So this picture here is a tensor network, a tensor description of a quantum manybody state, and that's innocent. Looking throughout the talk, I will be making use of this familiar picture of representing tensors as boxes with legs sticking out, and the tensor would have as many edges or legs as the degree of the tensor. So for n degrees of freedom, say in a quantum lattice model, one would have n legs sticking out, which would be the physical indices of the problem. So to characterize this tensor, one needs to know in n exponentially many complex numbers, so not so innocent after all. So the step to a matrix product state, MPS, or many paper state for good reason, is to take the scissors out and to cut this tensor into pieces and provide it with more structure. So there's an additional bond now, the virtual bond, capital D, which could be like 10, 100, 1,000, a finite number. So each site is associated with a tensor of degree 3, with a physical index going below and virtual indices going to the neighbors, which are contracted away to get the physical state vector of the manybody system. This looks like a small step. It's a structured tensor now, after all. But instead of having to store small d to the power of n many entries, one has of the order d squared, a capital D squared, d times n many numbers, so a linear scaling in the system size. And these states are indeed ubiquitous in good descriptions of manybody systems, as we will see in a second. They've been invented, to my knowledge, at least 3 times, as in the famous DMRG method, going back to Steve, then in finitely correlated states, and what mathematicians call tensor trains. So they are all mathematically equivalent, but to speak with Feynman, they're psychologically inequivalent. So there's something good to all of these flavors of pictures of matrix product sets. Well, that's great, but why would this be any good? The thing is that natural quantum states come with a lot of structure as well. So Hilbert space is in some sense a fiction. So natural ground states, in particular of gap phases of local, so short-range Hamiltonians, have in fact very little entanglement in the precise sense. So surely two-point correlation functions would decay exponentially with the distance in the lattice, but there's a stronger locality inherited by the locality of interactions, namely that there is what is called an area law for the entanglement entropy. So if I look at this kind of one-dimensional setting, or say at the half chain as depicted here, we can look at the reduced state of like some subsystem, and this reduced state will be a mixed state, even though the entire state is pure, that reflects the entanglement, say, over the cut in the manybody system. The upshot is that the entropy will, however, not grow extensively with the number of degrees of freedom, but only very little. Like the boundary area of that region, or like upper bounded by a constant in this half chain as shown in the slide. So the upshot is the entanglement entropy is like a boundary effect. There's much less entanglement in the system than there could be. And it takes a moment of thought that in fact MPS satisfies such an area law. In fact, log D, log capital D, is the largest entanglement that an MPS can accommodate by its very construction. But the interesting bit is that the converse is also true, at least in one spatial dimension, that every state that satisfies an area law can be well approximated by a matrix product state. So that's a bit of fine print, that is area laws with respect to Renyi entropies with a parameter smaller than 1, but the sense in which these matrix product states then approximate the true ground state is a particularly strong one in this set. So area law means that you can approximate the state vector with a matrix product state. And while this is this sounds may look basic, this is a quite profound insight in that it shows us that Hilbert space may be huge, exponentially large, but the states we care about sit in some corner. So the states that satisfy area laws, like the ground states of gapped matter, would sit in some corner, the physical corner, and the matrix product states basically capture this corner and largely parameterize those states that we are anyway interested in to spell out in the first place. So this teeny-weeny subset of matrix product states in some way parameterize the physical corner of area law states. That's in one spatial dimension. In two spatial dimensions, it still makes sense to think of projected entangled pair states, the natural two-dimensional analogs of MPS in two spatial dimensions. And while projected entangled pair states still satisfy area laws, the converse is strictly speaking not quite true. Like Yimin Ge and myself have constructed counterexamples some time ago, but morally it's still right that the projected entangled pair states nicely capture the meaningful area laws like physical corner of strongly correlated local interacting models. That is to say, tensor networks capture the low entangled states well, the states that are expected to be ground states of gapped phases of matter, of local Hamiltonians. It's kind of sitting there, and all these variational methods like DMG and variants thereof that we have seen many times already today and we'll hear much more about throughout the week are kind of variational principles based on this insight. Now, of course, this is true for like condensed matter local Hamiltonian systems, but what's in the focus of attention this week are systems of molecular quantum chemistry, which can, as a moment of thought reveals, be again, as fermionic systems, be written as spin models, if you want, by virtue of the Jordan-Wigner transformation. But then this is no longer a local problem, let alone a geometrically local problem. It's like an all over the place, everybody coupled to everybody type of problem. So to what extent are tensor network methods still applicable in the context of molecular quantum chemistry? And we will see that there's a kind of a freedom we can exploit. We can redefine the modes in the manybody system. That's a basic, very elementary thought, but interestingly, a quite powerful one in practical applications. So can we think of systematically exploiting the freedom of doing mode transformations to basically leave the physical corner and not sit in the low entanglement setting, but push things a bit and exploit this additional degree of freedom to formulate variational principles based on larger classes of states. This is for problems in like in global problems, say of systems in quantum chemistry. We will also have a look at problems in condensed matter systems of spinless lattice models and other applications in quantum chemistry, and also non-equilibrium problems, seeing that how one can not only look at static problems, but also systems of time evolution of non-equilibrium physics, again pushing the boundary and leaving the physical corner in some way. As I have already announced, I will use the final part of the talk to kind of meditate a bit more and look at further applications of tensor networks, somewhat superficially. I'm sorry again, but kind of further cooking up this theme of the physical corner when using tensor networks in somewhat less orthodox applications, say in the study of like quantum simulations, in machine learning and probabilistic modeling, in learning dynamic laws from data, and in, if time allows, holographic models of the ADS-CFT correspondence, and in capturing critical systems in a tensor network language. Okay, but let's get going on augmenting tensor networks with fermionic mode transformations. So the systems we have in mind are fermionic systems. So at each lattice side, say, there would be fermionic degrees of freedom. There could be 1 degree of freedom in a spinless fermionic model, or 2 in case of spin full fermions or p orbitals in one way or the other when we have some sort of local orbitals at the lattice side. For a for a lattice model, say the Hubbard model, thought to play a role in high temperature superconductivity, is maybe the holy grail type of a problem. But we are, of course, also interested in problems of molecular quantum systems in quantum chemistry, which in first quantization look as such, where we have, say, the distance between the electrons featuring in the Hamiltonian in this standard plain vanilla first quantized picture. Upon taking a set of orbitals, which of course is an art form in its own right, and we have heard and will hear a lot about this, how to like pick the active orbitals in the manybody system. It takes a moment of thought to see that in a second quantized picture, one gets the coefficients as suitable overlaps over these molecular orbitals, and then can find the structure problem of the electronic structure problem in second quantized form as a quartic polynomial that can be seen as a spin system on some lattice, except one, invoking a Jordan-Wigner transformation, which is by no means geometrically local, but these matrices would capture a coupling of all degrees of freedom to each other in some way. It should be clear at this point that naive methods to approach this problem are doomed to failure. There's a sense of dimensionality coming into play. This is exponentially large in the system size, in the configuration space. And the aim in a tensor network approach is to formulate variational principles that are reminiscent of CIS as post-Hartree-Fock methods, coupled cluster methods that complement density functional theory or dynamical mean field approaches in one way or the other. Now, as is, and interestingly so, because in the light of the fact that this is not a local Hamiltonian model, that everybody is coupled to everybody in some way, it's already true that variational principles based on matrix product states provide rather good approximations for systems in quantum chemistry, in that one can push bond dimensions to pretty high values, and this developed machinery of DMRG provides good numbers for problems in quantum chemistry. So ground state calculations can be done with 30 to 50 orbitals with bond dimensions in the 10,000s. One can capture strong correlation effects by this variational principle. It's a true variational principle, so all energies obtained are clearly upper bounds for the true ground state energy, which can be sandwiched with lower bounds if you want. But as a controlled and in principle even rigorous error bar in calculations, one can include symmetries like SU2, U1 point group symmetries in the problem to simplify things and really pushing it up to high bond dimensions. That's great. But some time ago, we thought, wait a minute, there's an additional degree of freedom that we can exploit, which is the very definition of what our fermionic modes are in the first place for a given set of active orbitals. So we can just say that we perform some mode transformation of the n fermionic modes as a unitary operation acting on our fermionic operators, which would in Hilbert space be represented by the metaplectic representation in fanciful terms. So that just means that you would make a linear transformation of one set of fermionic modes to another and redefine things in this fashion. It's of course a very simple idea, but actually a quite cute one in the sense that there's the manifold of matrix product states, which are agnostic to strong correlations and can perfectly well capture strong correlations in the problem, but they hate entanglement. So it's very costly to accommodate long-range entanglement in the system, whereas the manifold of fermionic mode transformations, or the metaplectic representation thereof in Hilbert space, they're completely agnostic to all over the place interactions, but they hate non-Gaussianity. So any Gaussian fermionic operation can be implemented in this fashion. And then they're kind of sandwiching the manifold of fermionic mode transformations from the bottom and having the manifold of MPS from the top gives a variational principle that one might think brings like both aspects of things nicely together. Now there's a bit of a devil in the detail in that one could think of like massaging the Hamiltonian beforehand or pre-processing the Hamiltonian. This is not so obvious after all. The energy landscape of meaningful cost functions is very rugged, and it's hard to find a global optimum of like pre-processing the full Hamiltonian so that afterwards the matrix product or the tensor network-based variation principle would work on top of that. This is conceivable, but does not work so well in practice. What does work, however, well in practice is to think of the joint manifold and along the way adapt the MPS manifold and the mode transformation manifold jointly, and then walk the manifold and make a joint update to accommodate both the entanglement through the mode transformation and the update of the matrix product state tensor networks on the other hand. So one thinks of adaptive on-the-fly mode optimization, transforming the Hamiltonian in this metaplectic sense and transforming also the state vectors using this mode transformation, like this UN freedom that one has. And one has to find a good figure of merit, like a good cost function here. Natural choices would be, say, the random entropy that has a location on how well one can approximate the state with a matrix product state. What turns out to be very well working in practice is a cost function that's based on a Renier 4 entropy, where one can also compute the exact gradient in an analytical form, the form of the Schmidt spectrum, and also kind of identify the tangent spaces and make, say, also conjugate gradient methods based on this this cost function to update the mode transformations along the way. So the algorithm is just to kind of iterate over neighboring sites, get the blocked tensors out, and then calculate this this cost function, then do like a conjugate gradient based update of the mode transformations along the way, and then calculate the new matrix product, the new matrices of the MPS, and then continue and then walk the manifold in a way in a downhill fashion to update jointly the MPS and the mode transformation manifold. So we've applied this to several problems in quantum chemistry, and this gives rise to actually substantially improved performance of this mode transformation augmented methods over matrix product states. So this picture here is, for example, for a beryllium-6 ring, where we see the energy over the presumed exact ground state for extremely high bond dimension of a setting with mode transformations, which gets an energy gap of 10 to the power -5 compared to 10 to the power -3 without mode transformations with the same bond dimension of 256, starting from a Hartree-Fock basis. So indeed, one gets substantially better energies using this mode transformations. What is also true is that one basically like disentangles the systems. That's not a rigorous statement. I mean, two-mode mutual informations have, strictly speaking, no direct implication on approximatability with matrix product states, but it's still an indicator of how this kind of uncouples the system, that over time, the system becomes less and less correlated, and the two-point mutual informations as correlation quantifiers become less and less, and the system kind of disentangles itself and becomes less correlated, so that the MPS can better approximate the ground state at hand. Over the time, so here, I mean, to look at the upshot, so mode transformations, they do improve the scaling of the bond dimension with non-local problems in chemistry. These are all over the place problems, not local Hamiltonian problems, and accepting that one can redefine the modes in a unitary fashion, one can do much better and improve the scaling of the bond dimensions and get a much better accuracy in energies with the same computational effort, basically at no expense from on the other side. And if one wants, one can also at some point fix the mode transformations and then run any state-of-the-art matrix product state solver on top of the found basis at hand. We've also over the years, I will only briefly show this for reasons of time, spent quite a bit on thinking about a rigorous underpinning of this when we, for example, thought about non-permutation-invariant Finetti theorems in the fermionic realm. Just to remind you, the Finetti theorems are basically the mathematical basis of mean field, and that if you have a permutation symmetric state of n particles and look at the reduced state of k particles, then this state is approximated by a convex combination of products with an error in one norm that scales like k over the number of particles, which basically says that if everybody is coupled to everybody, then a product approximation is a good one as an approximation of. Sorry. Sorry. Sorry, there was somebody at the door. As a mathematical justification of mean field. And here we find that if you have an interaction pattern of fermionic modes that is governed by a set of weighted indices, then the distance of the reduced state to a convex combination of products is again upper bounded by a number that is reflecting this interaction pattern. So lots of couplings, lots of neighbors lead to little correlations that motivate Hartree-Fock now in a precise, rigorous rigorously in the fermionic realm that justifies that if you have everybody coupled to everybody's system, then one would have a good approximation with low entanglement in the manybody system. So this is for non-local problems, but we also looked at this mindset for lattice models, they spinless two-dimensional fermionic lattice models, and seeing how well mode transformations can improve here things. And it's actually quite cool that it seems to help quite a bit. it is known that one-dimensional approaches give rise to quite competitive numbers. I mean, Steve White famously applied this to the Heisenberg model on the Kagome lattice, on using like a 1D snake to capture two-dimensional models at very high bond dimension. Clearly, one needs a very large and exponentially large bond dimension to capture the area law, because one needs to mediate nearest neighbors in the lattice through long snakes in the problem. But one could start in a snake basically, and then let the system adaptively find a good basis along the way, making a joint manifold optimization to see what the good basis is. The system likes to accommodate things to minimize the bond dimension of this one-dimensional embedding in the two-dimensional lattice system. It's a simple idea, but we were just too tempted to look at it and see what happens. And the outcome is quite striking in that the energies obtained are substantially better compared to the agnostic one-dimensional snake. So here, for example, this picture here shows like the energies obtained in an optimized basis for like 64 bond dimension. That's already way below the non-optimized energies for 512 bond dimension in the MPS. So again, the system would adaptively like to find the right mode decomposition, which is not a natural orbit, that's interesting, but it kind of finds a good compromise between locality and entanglement structure in the problem to find a better ground state approximation using matrix product state. That's a simple idea, but it seems to work quite surprisingly well. So this picture here shows not the energy, but the entanglement entropy of the half chain, which is the largest value one can have in the system. So one sees this as a one-dimensional system, cuts it in two, and looks at the entanglement entropy over the half chain as a function of the bond dimension. And interestingly, if you pump up the bond dimension, you would get a saturating value of the entanglement entropy in this two-dimensional system, like signifying a dimensional reduction in description of the manybody model, that a constant entanglement entropy is maintained while looking at a divergent entanglement bond dimension in the description. So that's interesting. So one finds a saturating von Neumann entropy for large bond dimensions in 2D systems. So in this sense, the adaptive mode transformation seems to find a good compromise between locality and entanglement in the system. It's kind of an effective dimensional reduction in description as the system kind of automatically finds it. Of course, one cannot find a full mapping of a two-dimensional general local fermionic model in two spatial dimensions to a one-dimensional local gapped Hamiltonian model with geometrically local interactions. There's kind of complexity theoretic obstructions against this because, well, one would basically find a polynomial time algorithm for a QMA hard problem, which is highly implausible. But it's still interesting to see that in practical terms, this simple idea of a mode transformation seems to give rise to good numbers accommodating locality and entanglement in the system. The final example I want to show is not related to ground states, but to time evolution, non-equilibrium properties of quenched manybody dynamics, where again, one starts off, say, in a product state and would look not at the ground state, but at the time evolving state of a setting that's generated by a local Hamiltonian in time. Now, indeed, short time evolution can be done with product state initially. One can easily, for short times, capture the non-equilibrium properties with tensor networks. In fact, in one spatial dimension, this is even provably the case, invoking the Robinson bounds and insights into approximations of states by matrix product states. This can even be pushed further, that one can really spell out the cellular automaton that captures the time evolution to cut a long story short, short-time evolution can be nicely mapped out by tensor network states. For long times, that's not true. Long-time evolution cannot be done because one can find a linearly growing entanglement entropy, Renyi entropy in time. That's not a bound. I mean, there's models that actually saturate this bound. This is actually happening. So that tensor networks can no longer accommodate these states. It's also true that, again, as a complexity theoretic argument, that time evolution is actually QMA hard. That's not so much known. It's interesting that a product state followed by a local Hamiltonian, and you measure out one qubit, is as good as a universal quantum computer. So that you can basically look at a reduction of a quantum computer to the setting, which means that there cannot be a classical efficient algorithm for all local time evolutions. And this devil comes out in different flavors, like in Monte Carlo, you have the sign problem. In DFT, you have like a stability problem. In tensor networks, you have the growth of entanglement entropy problem. So long times are, in one way or the other, a challenge to all kinds of classical simulation methods. That said, we were just too tempted to see what happens in a manybody system, guided by an example that I've shown many times before. I apologize, but it's just too cute not to show it. That was a support work for our friends at MPQ doing experiments with cold atoms and optical lattices that shows like a charge density wave 0, 1, 0, 1, 0, 1 initial state, followed by the bosonic variant in time, where one sees the non-equilibrium dynamics that saturates to half a particle per lattice site. But this picture not only shows the quantum simulation of a type, but also the classical resimulation using the same parameters that for bond dimension of up to 5,000, and the pedantism of Uli Schöllberg that was involved here, of the truncation errors involved, which would work to a certain point in time, which is great because the experiment runs on and you can ask questions about the physics of the problem better based on the experiment, the quantum simulation, than on the classical simulation that's basically done in order to build trust in the functioning of the device. But again, short times can be done, long times not. In our theme of the physical corner, we were just too tempted to apply this to the setting of fermionic non-equilibrium manybody systems. And this plot is somewhat preliminary still. We did this some time ago. This was a bit stalled for various reasons. We are just rerunning large-scale numerics on that. But it does seem that mode transformations seem to allow for substantially longer time evolutions, where you have your manybody fermionic Hamiltonian in some kind of interaction picture. You undo the entanglement with a Gaussian mode transformation, and then you only look at the entanglement growth between the modes in time that allows for longer times, because you're basically disentangling the system along the way at the expense of getting a longer range Hamiltonian, but you disentangle the system with the mode transformation, allowing for longer time evolution than before. So the lesson is, it's a simple idea, but fermionic mode transformations seem to allow to leave the physical corner for augmented tensor network studies. So there's this low entanglement physical corner, but by redefining fermionic modes, again, a simple idea, one has a pretty versatile tool to have a larger variation principle that seems to allow for good energies in a number of problems in quantum chemistry, in two-dimensional condensed matter systems, but also in the context of non-equilibrium problems. Okay, 33 minutes into the talk. So I will use the remaining time I have. I will stop at 50 to leave a bit of time for questions, to meditate a little bit around this theme of the physical corner, and, well, go maybe judge for yourself, go over a couple of applications where this idea of the physical corner appears in somewhat less orthodox applications of tensor net in various settings. And we will have a look at 3 examples of that kind. The first example is something we've been quite concerned with in recent time with our friends at Helmholtz Center in Berlin, in particular with Bella Lake, who's an experimentalist who speaks theory, which is wonderful, where we did support work for her experiments with actual real quantum materials and kind of tailoring tensor network methods for the specific experimental settings that they have in their lab. For example, they have their kind of a cute, funny double layer spin liquid, double layer Kagome lattice spin liquid, where there's a kind of new frustration mechanism in the problem, where we formulated not a PEPS method, but a projected entangled simplex state method that's really suitable for their geometry of the lattice at hand. And it's nicely scaling in the physical dimension so that the double layer can be seen as a four-dimensional local Hamiltonian problem, where we set up the tensor network simulation and could also find that the properties we identified in the classical simulation would largely match the experimental findings, say, concerning magnetization in the problem, not as a proxy abstract model, but really as I find that interesting, as a kind of simulation of an actual quantum material that they actually have in the lab, where they have also identified the ferromagnetic and antiferromagnetic bonds through neutral scattering in the problem, so that one can capture a proper quantum material using these tensor network ideas. Also with our colleagues in Garching, working with cold atoms and optical lattices, as mentioned earlier, we do quite a bit of support work on ideas of systems that bring in also interaction and disorder. So show features of manybody localization in, say, two spatial dimensions, where disorder can be incorporated by having extra degrees of freedom, so that the disorder average is achieved by tracing out these additional degrees of freedom and then getting the exact disorder average out at the end of the day. This makes sense also for corner transform matrix methods, not only for plain vanilla disordered systems, but also in driven systems or periodically driven systems, where one can think of, say, Floquet discrete time crystals in two spatial dimensions and see what tensor network methods have to say about this as a function of time. This is a long story. For the theme of our physical corner, what is interesting is that this gives rise to a situation where one can think of settings of Floquet time crystals as a blueprint in two spatial dimensions and see what's going on in what parameter regime. But the interesting situation is that one can devise schemes for time crystals, but only for short times. For the entanglement growth in the system, or for leaving the physical corner for that matter, one needs to go into the lab and needs to think of a NISC type, if you want, quantum simulation for intermediate and for long times, to see whether one would have a truly stable, not just pre-thermal time, discrete time crystal. So that gives rise to a blueprint for a quantum simulator, say with superconducting circuits or with quantum atoms in the lab. But one can look at the problem for short times with tensor networks to see what's going on here. So this nicely complements work done also by Roderich Mössner, who has spoken this morning as a kind of nice tool how tensor networks can help to devise a scheme, but that still give guidance that one needs to do the actual simulation of the actual problem in the lab using a quantum simulation of a kind. Then tensor networks in machine learning. This is a topic that is receiving a lot of attention recently, where deep neural networks are not tensor networks. It should be entirely clear, but there's more than a superficial resemblance of neural network with tensor network. And tensor networks, and people have looked at notions of supervised learning with quantum-inspired tensor networks, generative modeling using matrix product states, or actually using tensor networks in the head as a mathematical proof tool to look at the expressive power of neural networks in deep learning, but rather as a tool to find out how expressive the respective neural networks are. It's actually interesting to see that a number of settings ubiquitous in the machine learning context readily give rise to tensor. For example, probabilistic graphical models that are well, ubiquitous machine learning, in particular in image classification and so on, as a clever method to characterize dependencies of random variables, can be massaged and put together to find that these probability distributions actually readily give rise to a matrix product state, but not a quantum state, but a matrix product states where the physical legs are basically reflecting a probability distribution. So probabilistic graphical models readily give rise to tensor networks capturing probability distributions. The same is true for hidden Markov models. You can add hidden degrees of freedom and then see you still get as a distribution, as a probability distribution, again, a tensor network method capturing a probability distribution. Or short quantum circuits of the type, I mean, Frank has briefly mentioned them in his talk or at the beginning, what he would have talked about at the beginning. It's like these quantum supremacy circuits of having like a random circuit, how random circuits, and you make a measurement at the end. These are Born machines. It takes a moment of thought to see that if the circuit is not too long, you can contract them. That again gives rise to a probability distribution that is captured in terms of tensor networks. So graphical model, probabilistic graphical models, hidden Markov models, quantum circuits, they all give rise to tensor networks now capturing probability distributions. Now there's more than one way of writing probability distributions. For example, you can have a matrix product state or tensor train with non-negative real numbers that clearly gives rise to a probability distribution. You can also have complex numbers. You can think of pure states written as density operators. You can think of what is called a locally purified state or matrix, a positive matrix product operator, again over the real, non-negative reals, the reals or the complex numbers. There's many ways one can think of writing a probability distribution in terms of a tensor network. Interestingly, this is something that we've looked at in quite some detail with Yvonne Glasser, with Nicola Pancotti and Ignacio Sirac in Garching, where we looked at the precise expressive power of all these representations that are, for that matter, all complete, meaning every probability distribution can be written in this form, but there can be vast overheads from going from one picture to the other. So they are different in the expressive power of actually representing a probability distribution for a finite and fixed bond dimension. And this is a problem, it's a nice toy problem where the setting of expressivity can be fully and in all generality basically settled and brought to rest with quite big surprises in the expressive power in these settings. For example, when you write a probability distribution, it helps to write the tensors as complex tensors, even though the distribution you get, of course, is a real distribution. Somehow it seems to help to have complex valued tensor entries, even though you get a real distribution, and not only an advantage, this is an unbounded advantage in the system size. Why would that help? Well, it's probably the case. Or these positive MPO descriptions, they are also unboundedly better than any other tensor representation. And you think, why would an extra bond between two layers help to economically write a probability distribution? Well, that's probably the case. Ask me more, we want to hear more about the details. It's kind of a nice setting where one can really flesh out the power of writing probability distributions in terms of tensor networks. Building upon this and pushing this further, this idea of a physical corner, here we have a physical corner of probability distributions. You can also go further and say, oh, wait, how can I actually not learn distributions, but entire physical laws based on data? Say when Kepler stared into the sky and saw these funny points walking around and finding Kepler's laws, it took his genius to find out what these basic fundamental physical laws are based on data that he found by looking at these funny points on the sky. That said, if you think of a problem in biology or in fluid mechanics, it's far from obvious how one can learn the dynamical laws by observing a physical system in a data-driven fashion. And there's tools needed to find out what the underlying governing equations are based on data alone. And what people in theoretical and mathematical biology often do is they use for identifying the governing equations from observations. They looked at data from snapshots in time, like monitoring a physical system, and then recover the dynamical laws from data by taking a dictionary of basis functions, constructing a data matrix based on these basis functions, and then find the coefficient matrix that in a way best matches the data that you've observed in the lab. If you're fanciful, you can regularize this with a one norm, and this is called sparse identification. Never mind, what you basically do is you take a dictionary of basis functions and then you make a fit of the observed data, and this gives rise to the right-hand side of the differential equation of a nonlinear system equation of motion. That works beautifully. This paper here is much cited and much used in this context. Alas, it cannot be used for large system sizes for the obvious reason that, again, the curse of dimensionality sets in. So what can you do? What is a good hypothesis set for meaningful families of basis functions in the multipartite setting? Well, clearly you can take local function dictionaries and formulate a matrix product state or a tensor train based on that, and have meaningful hypotheses of manybody dictionaries of functions now in a scalable set. And this is an idea. Ask me if you want to hear more about this. This indeed gives rise to a scalable recovery of unknown physical systems from data, now not representing quantum states, nor probability distributions, but in fact, function dictionaries in a fashion where there's a kind of physical corner, namely the locally correlated function dictionaries, if you want, that resemble the same mindset as area law quantum states, short range probability distributions as a kind of local function dictionary in some way. And in practical context, ask me more if you want to hear more about this. One can indeed nicely scalably recover unknown equations of motion using like alternating least square methods together with tensor network dictionaries. The result I was maybe happiest with of the year in our of our group in the last year was on notions of quantum machine learning, if you want. That's a field that receives a lot of attention, maybe too much. I mean, that's a bit of a hype field where we didn't want to produce just pictures, but want to see, is there really something at stake here, in the sense that can there be a quantum advantage in a distribution learning of quantum devices over classical ones to kind of settle this conceptually speaking once and for all? And indeed there is in PAC learning, where you want to have an algorithm that takes samples from a generator, and with high probability, one should spit out new samples from a distribution that's close, approximately correct, to the given distribution before. And indeed, in this setting, one can find a provable exponential separation of the quantum task to the classical machine, showing that there, in fact, is scope for learning tasks. So quantum devices can actually provably perform better in learning tasks than classical machines. That's interesting conceptually. I should be very clear, this is not NISQ type yet. This is a full quantum algorithm of a full-scale quantum computer. What we are very busy with these days is to think of learning noisy quantum circuits of the type as Google has been investigating, or learning noisy circuits with other noisy circuits, where, unsurprisingly, tensor networks are the proof tool at hand. My last slide that I want to show here, so tensor networks provide beautiful tools in probabilistic modeling and machine learning. The last slide I want to show, and along the line of our theme of the physical corner and leaving the physical corner, is in looking at toy models for holography and the ADS-CFT correspondence that matches like ADS spacetime in the bulk as a Einstein gravity to a conformal field theory in the boundary, where match-gate tensor networks provide nice, efficiently constructible tensor network models that share many features of the real thing. Say the real Turk-Eigen formula, they can be mapped out in this setting. Interestingly, this is not only a numerical tool, but one can actually find full like conformal field theories and conformal transformations up to a quasi-crystal symmetry in these settings, and can find critical theories where one can really spell out the entropy formula of a system, not as a numerical thing, but one could, as an infinite sum, see the entanglement entropy formula of a conformal field theory in the manybody system, where one can even take the continuum limit. That's something we are doing with Alex Altland together, of a true quantum field theory in the boundary, where one can really not numerically but analytically spell out a critical state as a tensor network setting. Again, outside the physical corner, where one can go to a continuum limit of a quantum field theory in a largely analytical fashion. So I promise to stay within my 50-minute limit, so I like to keep promises. Let me stress that tensor network models can not only capture gap models, but one that also links to what Frank has said in the morning. One can also parameterize critical models here in an analytical fashion, which is simple enough where one can really do things not only numerically, but analytically. Tensor network models can also parameterize some critical models if one is careful enough. Which brings me to the end of my talk. So this was a talk when we meandered through the theme of accepting Hilbert space as fiction. It's large, it's huge, it's a very large vector space. Fortunately, the systems we are mostly interested in sit in some teeny weeny corner, some little patch, the physical corner that's characterized by area law entanglement scaling, which fortunately tensor networks seem to map out and largely parameterize to a good extent. For capturing models in quantum chemistry, it seems a good idea to push things a little bit and think of mode transformations that augment tensor network approaches. You widen the physical corner, have a larger variational set. It's a very simple idea, no doubt about this, but this seems to give rise to good data, good numerics, good understanding of using a tensor network manifold, but augmented by a mode transformation that, if suitably done as a joint optimization, allows for new insights in quantum chemistry, but also in lattice models beyond like 1D descriptions of 2D models, also in time evolution, of using like DMG type approaches in a 2D setting where there's a nice compromise automatically found between entanglement, locality in the system, capturing two-dimensional strongly correlated matter with a one-dimensional machinery. This was the main part of the talk, but meditating a bit more about the physical corner, we found that one can also think of the limitation of being constrained to the physical corner can lead to an interesting situation when we think of quantum simulations in NISQ type settings where we devise blueprints for actual quantum simulations in the lab. We've seen that this idea of a physical corner is matched nicely by not quantum states, but by probability distributions in the context of machine learning, or even function dictionaries in the context of learning dynamical laws from data, where this idea of a physical corner is again nicely matched out and nicely reflected now on different objects than quantum states. And very briefly, we found that also critical models, some critical states can be captured with tensor networks in tensor network models for holography. And with this, I would like to thank you very much for your attention. I'm looking forward to questions you might potentially have. Thanks for your attention.
All right, thank you very much, Jens, for that wonderful talk. And yeah, the floor is now open for questions. I see clapping hands.
Oh, thanks.
Questions? As to, oh wait, no wait. As to unmute. Yes, and can you speak, Mazen? I'm sorry.
You can speak, or you can also write this in the chat if you want. I can also see the chat.
Can you hear me now?
Oh, yeah, I can. That's
okay. Sorry, problems with my microphone.
Yeah.
I have a question about the physical corner. I think I didn't, there's a part that I didn't understand, because you said that if you do this mode transformation that you can leave the physical corner being the corner of area laws.
Yeah.
But isn't it that if you have something that works well with the mode transformation, then in a sense you have an optimized basis with an optimized ordering for which then either an area law or an area law with logarithmic would still be sites. So in that sense, you're still in the physical corner just with an optimized basis?
Oh, totally. That's precisely the point. Indeed.
Okay.
So I mean, on the level of state, that of course gives rise to a larger variational set. I mean, that's clearly possible. Just feed in a product state and look at an arbitrary Gaussian operation, then you have an arbitrary Gaussian state out that would, of course, violate entanglement area laws. But at the same time, you are also right that this is precisely what it does. It finds like a mode optimized picture, so that in this mode optimized redefined picture, you still find an area law for, or to a good approximation, area law for the resulting states in this mode transformed picture, so that the tensor network pictures nicely capture the state at hand. This is basically the entire upshot of things. So the prejudice overcome is that you shouldn't think in terms of local Hamiltonians, and then you can basically undo a lot of the entanglement in the system, say by letting the system find what it likes to be, to have it as short range entangled as possible, like in this 1D snake, where you really see how the system finds a base. That's actually interesting, because in 1D, there's basically the real space and the momentum space. There's not so much in the middle as an interesting realm. In 2D, you really see local bases adapting and forming itself, which is kind of intermediate. But you're of course right. The resulting state in the new picture is just basically like an area law state. So on a higher level, it's again a physical quarter. You're absolutely right. It's nicely put.
Okay. Yeah, thank you. That answers my question.
Okay, wonderful.
Right. There's another question from Emmanuel.
Yes. Can you hear me?
Yes, totally.
Okay, thank you very much for your pedagogical talk. So I also have a question about what you call fermionic mode transformation.
Mm-hmm.
So I'm a quantum chemist. So if I've understood correctly, what you talk about is what we call in chemistry orbital rotation, or a reoptimization of the orbitals, right?
Precisely, yes.
Okay. So now my question is the following. It's a bit like in the KSSF method. So I'm wondering what is actually happening, because when we try to describe strong correlation in a molecule, sometimes people try to localize the orbitals, because it's a smart way to actually get a more compact wave function, especially to describe strong correlation. So what is happening to your orbitals, basically? Are they localizing, or did you look at them? What really happens? Is this connected to this concept of localization?
Yeah, it is. It's very similar, but not quite. We had a similar intuition, and maybe also Ursh wants to comment on this. We had the same intuition that you get the localized orbitals, but you're not quite getting them. So we have no full interpretation of the orbitals that you get, except that they're the ones that happen to minimize our cost functions that allow for a good MPS-like approximation. So you are kind of getting localized orbitals in some way. Yes, that's true. But they're not fully one-to-one to the ones you would expect from other approaches. That's I think my answer to the question. But maybe Ursh, if he's in, also wants to comment from his perspective.
Maybe we can say that we are getting very close to split valence localized orbitals as well. So it depends, of course, on the problem. So I mean, there were different options to start from the Hartree-Fock orbitals, or after first Boy's localization, or using the split valence localized orbitals, using these orbitals as initial states, and then doing the mode optimization. Sometimes you get some small refinements also on the top of it. So basically, just starting from the Hartree-Fock orbitals, you ended up with this localized orbital picture. But of course, starting with already some localized orbitals, like the Foster-Boy's localization, you can still do some improvements. And in the 2D case, it again depends on the kind of on the strength of the interaction on the given phase. Because, for example, when in this 2D case, we chance showed that where you have this very large V, then a single determinant almost described the given state, because for large V, you get a charge density wave, and that was more or less a determinant with a single determinant describing the state already get you the correct state. This is why the entropy was almost 0 in the figure for large V, and then it's also 0 for V equals 0, because then you get just the momentum space description. So it's really just a dynamic way to find the given modes, but this is sometimes the localized ones, sometimes you get some delocalized ones.
Indeed. So I mean, but they're not the localized one as one commonly calls the, but not necessarily so. Also, like in 1D, as I briefly hinted at, you can also find a switch from real space to momentum space, where the system would automatically find either way. So this can also happen, that really have a bimodal switch of one world or the other one, and there's nothing in the middle. Sometimes you find nice compromises in the middle. That's kind of a cute picture.
Very nice. Thank you very much.
Thank you. Thanks for the interest.
All right. Are there any other questions?
Yes,
from me.
Yeah.
Yeah. Can you?
Hello, I can hear you. Just ask ahead.
I've just written in the chat because somehow my raising hand does not like to work. Thank you very much for this talk.
Yeah,
towards the end, you mentioned that we can try to find information on the basis of a dictionary of functions that we provide for learning about a problem or about the information in the problem. My question is, how good do we need to be in designing this dictionary of functions if we wish to study a problem? Trying to make a very simple example, if we start on something which is dependent on just a single coordinate and we would be able to use functions of that single coordinate, we could start with monomials, then we could switch to algebraic functions, including rational exponents. But if we stop there and our problem would require a logarithm, we would never get it.
That's precisely right. I mean, of course. Yeah, this is a wealth of questions in one shot.
Sorry.
These are highly exciting questions. Maybe I filter out two types of questions. I mean, both of which I cannot fully answer, I should say. That said, the one question is, like, for a given function dictionary that that's like you said, like, what's the expressive power of this kind of function dictionary? Yeah. And that's kind of the analogous question to what we know in quantum physics, where we know precisely well what the expressive power is, right? I mean, we know, I mean, I don't need to teach you, I mean, all this ideas of entanglement area laws, blah, 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 we know how well you could approximate, well, you know all this. In probability distribution, that's already more subtle, and I hinted at this work with Yvonne and Nicolas and Ignacio, that shows that, for distribution, that's already more subtle, actually, in some way. For function dictionaries, it's even more subtle because that's the question of function approximation. That's not so obvious, and we are just joining forces with the mathematics department at TU using like splines of how well you can think of a notion of function expressivity for a given dictionary. Now, it can of course also happen, that's your second point, that your function is so funny that you cannot well approximate this with any element in the function dictionary. What happens then? And then the question is how well you can say a posteriori, using correlations, find out how much you have failed in your approach. You know what I mean? You must fail. I mean, you've hinted at an example yourself, and with the log, where no matter what monomials you put in, you will never really hit it. At some point, you will say, you would want to have a picture where you say, wait a minute, this is not going too well. That your machine says, oh, beep, red light, I'm not doing it. And there seems to be hints that this works as well. But none of these things are fully understood. We're just progressing here, but we are taking steps in the expressivity question, where we have some first insights. But practically, it often works quite well. I mean, this I should say, that if you take like a coupled chain of non-linearly coupled beds and springs and so on, you look at data and it nicely recovers the Hamiltonian at hand, which is kind of cute already. But this is a very practical mindset. As you might have seen, I also like to prove things if I can. Here, this is not in theorem land yet.
Thank you very much.
Yeah, wonderful. That's wonderful questions. Yeah.